Welcome back to Logic, Language and Information. In this, the last of the lessons on digital systems, we will examine how to find minimal DNF circuit designs for combinational systems. The purpose of the minimisation is to ensure that an implementation in standard two-level DNF form will use up the least amount of space on a computer chip. So let's begin. Recall from last time that a minimal DNF circuit will have the minimal number of inputs to the one OR gate at the outer level, and at the inner level, the AND gates with the minimum number of inputs. The Karnaugh map method is a systematic method for finding a minimal DNF logic formula from the truth table for a propositional logic formula or a combinational system. It is a graphical, drawing-based method limited to 6 inputs or atomic propositions. Karnaugh maps are called K-maps for short. We'll only see K-maps with 3 or 4 inputs. The method was first developed by Edward Veitch in 1952 and refined by Maurice Karnaugh in 1953, suitable for up to 6 atoms or inputs. In 1956-57, it was generalised by philosopher-logician W.V. Quine together with mathematician-engineer E.J. McCluskey. The Quine-McCluskey algorithm for finding minimal DNFs in any number of atoms is still a core tool within electronic design automation tools today. To begin with, a K-map should be thought of as a compact truth table, as just a graphical rearrangement. Take an 8-row truth table, such as the one for our 2N MUX system. We take those 8 rows and rearrange them in an 8-cell 4x2 grid. Just for now, ignore the strange ordering of the cells in the 4x2 grid. We'll come back to this in a minute. As in a truth table, the cells are labelled according to their input combination. 2-bit codes for inputs X and Y label the 4 rows of the grid, and 1-bit values for input S label the 2 columns of the grid. The bit value entries inside the grid cells are the values for the output Z. In the truth table, output Z is 1 in 4 rows, those numbered 3, 4, 6 and 7. Highlighted in grey in the table. In the K-map, there are likewise 4 cells containing bit value 1, here marked in red. The cells indexed by 3, 4, 6 and 7, which correspond to 3-bit XYS codes 011, 100, 110 and 111. Another example, take a 16-row truth table with 4 inputs A, B, C and D and 1 output Z. We take those 16 rows and rearrange them into a 16-cell 4x4 grid. Stay with me and keep ignoring the strange ordering for now. We'll come back to it. As in a truth table, the cells are labelled according to their input combination. 2-bit codes for inputs A and B label the 4 rows of the grid, whilst further 2-bit codes for inputs C and D label the 4 columns of the grid. Again, the bit value entries inside the grid cells are the values for output Z. In the truth table, output Z is 1 in 6 rows, those numbered 0, 1, 2, 3, 11 and 12. In the K-map, there are likewise 6 cells containing bit value 1 marked in red, the cells indexed by 0, 1, 2, 3, 11 and 12. At this stage, we can see that a K-map contains all and only the information contained in the corresponding truth table. It is just a rather peculiar reordering and rearrangement of the truth table. Now, this very peculiar ordering of cells in a K-map is designed so that any 2 adjacent cells reference rows of the truth table that differ only on one atom. What's called the grey code is an ordering on 2 bits as follows. It's a ordering on 2 bits in cycling order. 0, 0 goes to 0, 1, goes to 1, 1, goes to 1, 0, goes back to 0, 0. It has the property that any pair of adjacent 2-bit values will differ only on one of those 2 bits. This code is used to index the size for side of a K-map grid. In the 2-dimensional K-map, we have several different ways in which cells can be adjacent. There are vertically adjacent cells, there are horizontally adjacent cells, and there are wraparound adjacent cells, both vertically and horizontally. The Karnaugh map method to find minimal DNFs involves drawing loops around ones in the K-map. We start by identifying all the ones in the K-map, just like identifying all the ones in the output column of the truth table. We then try to cover all the ones in the K-map using loops of 2, 4, 8 or 16 pairwise adjacent cells containing 1. The key to the method is to 1, use as large a loop as possible, and 2, to use as few loops as possible. Loops or groupings of pairwise adjacent cells must be of size a power of 2, so that 1, which is 2 to the power 0, is okay, as well as 2, 4, 8 or 16. The last resort is a loop of size 1. Looping the ones in a K-map is a graphical way of describing the simplification of complementary pairs of truth table row conjunctions that differ only on one atom. The number of loops will correspond to the number of inputs to the OR gate of the DNF circuit, so we want as few loops as possible. Each loop will correspond to an AND gate. The larger the loop, the more cancelling of atoms, and so the smaller the conjunction. The loop itself contains all the information needed to determine the conjunction corresponding to the loop, and thus the inputs to the AND gate. Let's go back to the 8-cell 4x2 K-map for the 2N Mach system and look at those 4 ones. We can cover the 4 ones with 2 loops, one looping cells 6 and 4, and the other looping cells 3 and 7. Notice that we could have also looped together 6 and 7 going sideways, but that wouldn't add anything extra. It would just give us an additional loop that isn't needed to cover the ones. So 2 loops gives us 2 disjuncts in our minimal DNF. Let's see how we found them and how the looping corresponds to the Boolean algebra simplification we saw last lesson. First, the loop of cells 6 and 4. Cell 6 has the 3-bit XY S code 110, representing X and Y and not S, while cell 4 has the 3-bit code 100, representing X and not Y and not S. These 2 cells are complementary with respect to Y, so that the Y's are cancelled to end up with the conjunction X and not S. The second loop, the loop of cells 3 and 7, for that loop, cell 3 has the 3-bit XYS code 011, representing not X and Y and S, while cell 7 has the 3-bit code 111, representing X and Y and S. These 2 cells are complementary with respect to the X input, so that the X's are cancelled, and the result is the conjunction Y and S. So the resulting minimal DNF circuit has an outer 2-input OR gate and at the inner level 2 2-input AND gates, as we claimed last lesson. Next example, our 4x4 K-map. This one has 6 cells containing 1s, and in this case we can cover them using a total of 3 loops. First, we get a size 4 loop around cells 0, 1, 3 and 2 across the top. Since 0 is adjacent to 1, 1 is adjacent to 3, 3 is adjacent to 2 and 2 is adjacent to 1 via the wraparound. In this size 4 loop, both the C's and the D's are cancelled, and the remaining code of 0 for A and 0 for B tells us that we have the conjunction not A and not B. Second, the size 2 loop of cells 3 and 11, which wraps around vertically. These two cells are complementary with respect to the input A, so we can cancel the A's, and the remaining BCD code of 011 tells us that the conjunction is not B and C and D. Note that a size 2 loop of cells 3 and 11 is better than a size 1 cell of loop of cell 11 on its own. Notice also that cell 3 is now covered by 2 loops. That is fine because it's resulting in larger loops. Finally, the last lonely cell is the 1 in cell 12. It has no adjacent cells containing 1s, so we cannot loop it together with any other cell. We have to take the last resort of a loop of size 1. The ABCD code of 1100 tells us that this conjunction is A and B and not C and not D. The resulting minimal DNF circuit, which you can draw on your own for practice, has an outer level 3-input OR gate and at the inner level a 2-input AND gate, a 3-input AND gate and a 4-input AND gate. Now it's time for you to get some practice looping K-maps yourself. This K-map for output Z, depending on inputs A, B, C and D, contains a total of 5 1s in cells 1, 4, 6, 12 and 14. Your task is to use as few loops as possible and as larger loops as possible to cover these 5 1s. Then translate your loops into conjunctions to get the minimal DNF. How did you go? For this one, we can take a size 4 loop to cover cells 4, 6, 12 and 14 using a horizontal wraparound. In this size 4 loop, both the A's and the C's are complementary, so get cancelled. The remaining code indexing B and D is 1 and 0 respectively, so we get the conjunction B and not D. That covers 4 out of 5 of the cells with 1. The last one, cell 1, is the lonely one, with no adjacent cells containing 1s, so we cannot loop it together with any other cell, and we are left with the last resort loop of size 1. This cell has the ABCD code of 0001, so it corresponds to the conjunction not A and not B and not C and D. If you have any more questions or comments, first take a look at the course notes and then head into the discussion boards, and I'll check in on the discussion there. We do need to be clear that the Karnaugh-Veitch mapping method, or more generally the Quine-McCluskey algorithm, only concerns DNF circuits and not arbitrary logic circuits. Similar to an example we saw last lesson, the formula P and S or Q and S is a minimal DNF for the system shown, as is easy to demonstrate with a 4x2 K-map. Hence, the circuit as shown, consisting of a 2-input OR gate fed by two 2-input AND gates, is a minimal DNF circuit. However, we could apply the tautology expressing the distribution of OR over AND in order to further re-express the formula as P OR Q and S. This results in a circuit with only one OR gate and one AND gate. Yes, this circuit is smaller in gate count, but at a cost. It is not in DNF form. So, we'll finish off this lesson by gaining more practice with K-maps via a decoder or display system. We want to display on a 7-segment device any one of the decimal digits 0, 1, 2, 3 and so on up to 9. These sort of 7-segment displays are usually made of LCDs or LEDs. For example, suppose we hooked it up to the BCD encoder from last lesson, which turned a keypad decimal digit input into a 4-bit binary code. Pressing the keypad button 3 should light up the 5 out of 7 segments that form the shape of the symbol for 3. For all 10 decimal digits, here are all the patterns needed to form those symbols on a 7-segment display. Notice that the patterns are all distinct, and it is only the 8 that is required to light up all 7 segments, and all the other numbers leave out at least one segment. Notice also that we have to agree on the pattern for the number 1, choosing to align it to the right of the display rather than, say, the left. The 7 segments are labelled A, B, C, D, E and F. The 2 segments needed to be lit up for symbol 1 are B and C. Now, our BCD to 7-segment decoder is a system with a total of 5 inputs and 7 outputs. It is required to take as input a 4-bit binary code M equals M3, M2, M1, M0, together with a 1-bit control input R, and return as output a 7-bit code A, B, C, D, E, F, G, which encodes how to light up the 7-segment display by turning on or leaving off the various segments. The functional description is as follows. If the 4-bit binary code M is in BCD form, binary coded decimal, having decimal value in the range 0, 1, 2, 3 up to 9, and in addition the control input R is 0, then the intended lighting up of segments as shown earlier is to be effected. Otherwise, if either the 4-bit code M is not in BCD range, or the control input R has value 1, is active, then none of the 7 segments are to be turned on. By combining the BCD encoder from last lesson with this BCD to 7-segment decoder, we could then simply create a decimal keypad to 7-segment display codec circuit by connecting outputs of the first with inputs of the second. For example, if button 7 on the keypad is the only button cleanly pressed, then input signal P7 will be the only input active for the BCD encoder. The resulting 4-bit output code M equals 0111 and the error output R equals 0. Then the BCD to 7-segment decoder will activate outputs A, B and C to light up the display to form the symbol 7. On the other hand, if the keypad is mishandled and 2 or more buttons are pressed, then the BCD encoder will produce an error output R equals 1, which would then be passed on to the BCD to 7-segment decoder, resulting in no segments being lit up. Now, the truth table for the BCD 7-segment decoder is as partially shown. Given 5 inputs, it should be 32 rows. For the intended lighting of the decimal values 0 through to 9, as shown in the first 10 rows, as listed here, you can check that we have the right distributions of zeros and ones. For example, take decimal 5, that should light up the segments A, C, D, F and G. We go into the truth table and yes, A, C, D, F and G are to be activated. For the remaining rows of the truth table, remember that we use a bold X to mean don't care, so the bit value can be either 0 or 1. When the decimal value of the 4-bit input M is between 10 and 15, we don't care whether the control input R is 0 or 1. Either way, the output is all zeros and no segments are lit up. Likewise, when the control input is R is 1, the value of M won't matter, as in all such cases, the output is all zeros and no segments are lit up. The BCD 7-segment decoder gives us 7 examples of 4x4 K-maps to play with. For each of the outputs A, B, C, D, E, F and G, we can use a 4x4 K-map to derive a DNF formula for the output in terms of the 4 main input bits, M3, M2, M1 and M0. Additionally, from the truth table, we can see that we also need to add an extra conjunct for not R to include the dependence on the 5th input, R. So first, we'll start with the A output. We begin by just taking the bit values in the A column of the truth table and mapping them to the corresponding cells in the 4x4 K-map. We have 1s in rows or cells, 0, 2, 3, 5, 6, 7, 8 or 9. There's a total of 8 of them. Note that in the canonical DNF, this means we would have a size 8 disjunction. Next, we start looping. The biggest loop we can get here is of size 4, covering cells 3, 2, 7 and 6. For this loop, M2 and M0 are cancelled, and the remaining bit values for M3 and M1 are 0 and 1 respectively. So combining with the extra conjunct not R, we get the conjunction not M3 and M1 and not R for this loop. The size 2 loop of cells 0 and 8 cancels M3, and the resulting conjunction is not M2 and not M1 and not M0 and not R. The size 2 loop of cells 5 and 7 cancels M1, and the resulting conjunction is not M3 and M2 and M0 and not R. This size 2 loop around cells 5 and 7 is better than a size 1 loop around cell 5 on its own. And then finally, we have the size 2 loop of cells 8 and 9. This cancels M0, and the resulting conjunction is M3 and not M2 and not M1 and not R. Again, this size 2 loop around cells 8 and 9 is better than taking a size 1 loop around cell 9 on its own. Again, notice that it's okay to cover some cells by 2 loops. Here, that's the case for cells 7 and 8. This is fine because it's resulting in larger loops. Our minimal DNF gives a circuit with an outer level 4-input OR gate, and at the inner level 1 3-input AND gate, 3 4-input AND gates. This minimal DNF is certainly not unique. We could have replaced the loop around cells 0 and 8 with a different one going sideways around cells 0 and 2, but the sizes would have all come out the same. So very quickly, we'll go through 2 more outputs from the BCD 7-segment decoder. You'll be able to pause the video and study them more closely for yourselves. For the C output, there are 9 rows of the truth table in which C is 1, and these are all of 0 up to 9 except for 2. 3 loops of size 4 will cover all of these, and that's the best that can be done. The resulting minimal DNF for output C is as shown. And for the E output, there are now only 4 rows of the truth table in which E is 1, 0, 2, 6 and 8. These can be covered by 2 loops of size 2, and that will be optimal. The resulting minimal DNF for output E is as shown. So that brings us to the end of this lesson and to the end of the lectures for this application section on digital systems. The course notes, practice exercises and assessment tasks will introduce you to some more examples of combinational digital systems. With more examples, you'll get more experience working with the various different ways of representing combinational systems. Functional descriptions, truth tables, now K-maps, logic formulas and logic circuit diagrams. In our successor offering on Coursera, the subject Logic, Language and Information 2, there will be a further application section on digital systems that will delve further into the topic, including introducing sequential digital systems with memory, delay components and feedback loops. If you've become really intrigued by this topic and want to study further, I recommend a beginning level 8-week undergraduate course on digital systems offered on Coursera and taught from the Autonomous University of Barcelona, with the link as shown on the screen. Thank you for your attention and interest. I hope you've enjoyed this introduction to digital systems and their foundation in logic, and I hope you go away with a basic understanding of the topic as befits an educated person in the 21st century. Cheers.